Welcome back. Now we are going to look at the change in the property upon mixing components. So, let us consider a mixer, okay, where various different components are getting mixed at temperature and pressure, okay, and what you get is basically a mixed fluid at temperature and pressure. And the question which you are asking is the change in quantity or property E on mixing. Okay. So, you are asking like what is a typical change in E? E could be entropy, AQP, enthalpy, Gibbs free energy and so forth. So, let me first define this, which is basically the delta E mix, which is nothing but the change upon mixing. So, this would be E, which is a property of the mixture at Tp and with all composition minus summation of Ni number of moles and individual component molar property at temperature Tp. Okay. So, this is basically by definition. I can divide by total number of moles and also can write in small e mix. Now, in this case I am not making very strong statement by changing y's to x. Okay. So, it is just a composition at this point. Usually x is represent the composition in liquid phase and y represent composition in a gas phase, that is by convention, but at this point it is just a composition in the mixture. Okay. Now, let us consider an adiabatic process and steady state. Okay. Now, if you consider adiabatic process, you can write down your first law in a continuous mode or flow system, Q minus W plus summation N in H in minus summation H out N out H out. Okay. Now, for being adiabatic, of course, and there is of course, we are saying that there is no work associated with it, and what you see here is the temperatures are constant here. So, this is the component which is of the system, which is let us say in this within this mixture. Okay. Now, being a steady state, the changes are going to be 0 because all the properties are going to remain constant and hence the change is 0. So, this must be 0 of the system within the mixture, right. There is no work associated, the boundary work, no other work is associated. So, we are going to make this to be 0. Now, we are going to say is that well Q is nothing but essentially the enthalpy of the mixed fluid at Tp minus summation N in H in Tp. Okay. So, this is basically for pure component, H in means it is like a for pure component. I can actually write this more in the language which we are being using here, Hi. Okay. So, Q is basically has to be 0, that is what we are saying. Q is nothing but whatever the changes we are occurring, since is adiabatic, Q need to be 0. Okay. So, this is a generic expression. So, this would be nothing but your delta H actually makes, right, considering by definition. Now, if Q is positive, it means exothermic. If Q is negative, it means endothermic, right. Now, if it is adiabatic, it has to be 0. Now, in order to maintain it, since there is no way to extract the heat out of the system, if it is an exothermic, the temperature will change of the system. Okay. So, but then it depends on what is the typical delta H mix. So, it depends on whatever the temperature, whatever the changes occurring depends on T P X I. Okay. So, for adiabatic, of course, this must be 0, right. Okay. So, what is the typical temperature of the system will vary, and how this vary with the composition. It will also vary with the system which you are considering. Okay. So, let us try to understand it a little bit with an example. So, I will just go through an example for the same system which is an adiabatic and ask questions related to the temperature, but before that let me just give you what is a typical delta H mix, okay, for a binary system. Okay. So, it is not like monotonous, it is quite complex, and it depends on, as I said, temperature, pressure and composition. Okay. So, this is an example of a binary system, binary liquid mixture, okay, which means basically we can write like this for water and ethanol. Okay. So, this is a water, ethanol system, and the data are taken from a paper, a journal paper, which is a Journal of Chemical Thermodynamics. Volume 7, page 137 to 148, 1975. It is very old though, but nevertheless it gives an idea what we intend to learn from here. So, let me just draw, again it is not on perfect scale, but it will give us the idea. So, this is X, which is a composition in this binary mixture. Okay. So, this is 1, 0, so 0.2, 0.4, 0.6, 0.8. Okay. This is somewhere it is 0, and what I am plotting is basically delta small h mixture. So, basically the change in the property, change in the enthalpy per mole. Okay. So, this is the unit is joules per mole. Okay. Now, I am going to draw these values with changes in the temperature. So, this is a typical value for 380 Kelvin. Okay. This is how it looks. This is close to 800 here, minus 800, and this is close to 600 here, plus 600. This is 0. Okay. And the temperature here is 300 Kelvin. So, as you see, it is quite non-monotonous, it is quite varying, and now if you have been given such a data to make use of it to calculate certain changes in the temperature in the system, how are you going to do that? So, let me just use this data to and then pose a simple question to you, and the question is the following, that we need to calculate the temperature rise within 1 Kelvin accuracy, okay, when 0.8 moles per second of water are added to 0.2 moles of pure ethanol. Okay. And the condition is that it is a adiabatic continuous flow process. Now, both the input streams are at 300 Kelvin and 1 atmosphere. Okay. So, you have been asked to this particular question. Now, the data are given here, though it is not on scale, but I have the numbers with me. So, what information we have is delta H mix at 0.2 mole fraction and temperature 300 Kelvin is minus 750. So, this is basically X of ethanol. Okay. So, this would be your X ethanol. So, somewhere at 300 it is around 750 joules per mole. Okay. 750 joule per mole. What does that mean? It means being is negative, changes in enthalpy, it means the heat is being generated. Okay. So, which means considering that the process is adiabatic, the temperature is going to rise. Okay. There is no way you can extract the heat out of the system, the temperature is going to rise. So, we need to find out the temperature. Okay. So, how are we going to solve this problem? So, you are only given delta H mix. Okay. So, other thing which I can provide is basically Cp also. So, I can give you the information of Cp. So, from NIST Web of Science or NIST web book, okay, which you can type it on internet and you can get this information, is free of cost. Cp for 1, which 1 is your ethanol and 2 is your water. For pure ethanol at 300 Kelvin, Cp1 is 112.4 joules per mole Kelvin, and Cp2 is for pure water is 300 Kelvin, 75.3 joules per mole Kelvin. Okay. So, this information is given to you. Now, how are you going to calculate your temperature? So, when you said the first part, actually what you meant that, so let me just describe the idea. This is what you have done is perfectly fine. So, the idea to solve this is we have to make use of the fact that enthalpy is a state function, path is independent and is independent of path. So, what we are going to do is that we will consider that component 1 at Tp and component 2 at Tp is taken from temperature to the final temperature. Okay. And here we are going to mix it. Okay. So, and then enthalpy, the other important thing which we are going to assume by taking this approximation from where we are going to write the enthalpy change as Cp delta T is the fact that enthalpy is a weak function of pressure for incompressible fluid. Okay. So, with this, so what we are doing is basically we are taking component 1 to T final, which we do not know, okay, and similarly component 2 taking to T final, and then we are going to mix it. Okay. So, with this we have this composition of ethanols X multiplied by Cp 1 delta T plus 1 minus X Cp 2 delta T. Okay. This plus whatever the change in the enthalpy due to the mixing, this must be 0. Okay. Why? Because Q is 0. Okay. This comes directly from our previous exercise. Now, with this we are going to write this expression as minus of delta H mix plus X Cp 1 plus 1 minus X Cp 2. Okay. Now, the key issue is what would be our guess value. Okay. So, what we have been given is this information. We can look at this graph, and we can start from 300. Okay, assuming that small changes are there, that maybe this output stream is also at 300. So, at 300 for 0.2 composition, because composition is fixed, okay, because 0.2 ethanol is there, minus 750 is our delta H mix. So, when we put that delta H mix for 300 Kelvin, we get as 7 Kelvin. Okay. Now, which essentially means T final is 307. Okay. Then, so T final is 307. So, this is our first iteration. Okay. Now, we again go back and find out our delta H mix at 0.2, T is equal to 307 Kelvin. We look at the graph, it turns out to be 640 joules per mole. Okay. We plug in back this in this equation, we got delta T as 6 Kelvin. So, the change from the first iteration to the second iteration is 1 Kelvin, and thus since the question was that within 1 Kelvin accuracy we wanted to find out the temperature rise, we can stop here because we have got a value, okay, which is 6 Kelvin. Okay. So, we got the change in the delta T temperature at 306 Kelvin. Okay. So, this is how we make use of these expressions in order to solve problems using the experimental data as well as the first laws as well as the basic definitions. So, this is only at 300 Kelvin. So, what we are assuming is basically also that Cp is a weak function of temperature, that within small variation it is not changing, it is almost constant. Okay. So, we can stop here now, and in the next lecture we will take another example, try to exploit further understanding of partial molar properties. Okay.